thought it'd be fun to look at a molecular dynamic simulation of psilocin bound to the serotonin 2A receptor. The entry for this is gonna come from a Brian Roth crystal structure publication. I believe Gumper's also on this, who was Brian Roth's a PhD student who's now a faculty member at UNC Chapel Hill. The PDB ID that I'm using for this particular project is, it's this one, 9AS8. It's from a 2025 crystal structure paper. I'm just going to reset this to default. Okay, this is the crystal structure as is from the PDB, and the binding pose makes sense for psilocin. Psilocin is an indole-based psychedelic that comes from psilocybin, which gets metabolized where the phosphate group breaks off of this position right here and becomes an alcohol and during metabolism. So when psilocybin, when you consume it, the phosphate group gets cleaved off. It turns into psilocin, which is the molecule that is psychoactive that gets the brain to produce intoxication. It's a pretty clean crystal structure, things that you would expect. You have this hydrogen bond right here in the PDB ID. Okay, and that hydrogen bond is occurring at, we can measure it. It's occurring at a distance of 2.35 angstroms, which makes sense for hydrogen bond. You have this pi-pi stack between the aromatic ring and the phenylalanine 240. Let's just give it a measure using the measure tool. Okay. Excellent. 5.02 angstrom for the T-shaped pi interaction we have here. The salt bridge that you always see in GPC. Well, I'm not going to say GPCRs. The salt bridge that you always see in quite a lot of GPCRs between a positively charged amine and a carboxylic acid. Let's just measure that one. Let's try that. Much better. 3.21 angstroms. Okay. The tool that we have to use to run MD is called Desmond. You can only run MD on a Linux-based system, so you can't run this on Windows. The first thing you need to run MD is a tool, well, the output file. Name of the job is System Builder. For membrane, if you know anything about G protein coupled receptors, they sit on a cell membrane, which means that we do have to put a membrane in. I'm going to set up the membrane. If you go to place automatically, it'll put it on the helices, and it does a pretty decent job. So I'm gonna hit save membrane position. I'm gonna hit OK. Okay. For box shape, I'm going to use orthorhombic. It'll show the boundary conditions right here. It's basically going to put lipids over here and then waters in every other position around in the box. I'm going to run this job, Desmond setup. I'll call this 9AS8. And I'm going to hit run. View in project. And if we notice, what did it do? Well, it made our simulation box. In our simulation box, once again, you can see the boundary conditions outlined in red here. You can see the lipid bilayer, right? These are all the lipid bilayer over here, all the lipids, and then waters in every other position. Now we have to actually run the simulation using Desmond. I have to hit load from workspace. Hit load. Okay. For total simulation time, most academic publications use 100 nanoseconds. That's what I'm going to use. I'm not going to change anything else for now. I'm going to leave everything else default. Okay, this is 9 MD. This is 9 AS8. You do need a decent graphics card for this job to run. If you have a lower end graphics card, it will run. The runtime will just take longer. This particular remote computer that I'm running on runs an RTX 3060 Ti, which is actually my favorite graphics card overall. Price to performance, I really like the 3060 Ti. Okay, we can always monitor the job, and I'll see you guys back when the job finishes. Okay, here I am some hours later. The job has completed. It has taken a total GPU time of 7 hours, 16 minutes, and 18 seconds used by 7 subjobs. The lower on your graphics card, the longer this will take, but I mean, you can pick up graphics cards for not that expensive even by today's metric. But honestly, with all the data center stuff going on, RAM and NVMe drives are getting quite expensive, and I wouldn't be too surprised if graphics cards get expensive, kind of like they did in 2020 because of GPU mining. So, anyways, 7 hours later, this job is done. Let's take a look. Let's go to our output file. Okay, here's our output file. I'm going to close out the MD system builder so I don't get that overlay in there. Here's what it looks like when it's done. Oops. And if we play the simulation, okay, let's zoom into the actual active site. I'm going to hide the waters and the lipids so that I can see everything a little bit better. I've done that over here in this trajectory file. Okay, let's zoom into our ligand. That's ultimately what we care about. Okay. Kind of like this pose view right here. Let's play it. If you want, once again, to look at how the bond distances are increasing in real time, as you run the simulation, you can put those in the measure tool, just to illustrate. And you'll notice that as I play the simulation, you'll see that number constantly change. Right? You see this hydrogen bond distance change. And you can do the same thing with, let's say, a pi stack. Okay, I just wanted the one with the dual pi stack. There is a lot more to reading MD output files than this, but in this video I just wanted to show you how cool microdynamics looks. Till next time, Hope you guys enjoyed this one. Bye-bye.